Hello everyone, and welcome to our webinar today. Today we'll be covering filtration and flow control basics in advanced porous metal media for aerospace and defense. And I'd like to introduce you all to our speakers today. First we have Tim Goodart. Tim, you want to say hello?
Hey everyone, glad you can make it.
Tim has been an applications engineer with Mott for about 15 years. And I believe you've designed maybe thousands of porous metal components in that time for our customers?
That would absolutely not be inaccurate.
Okay. And additionally, we have Al Morena. Al, you want to say hello?
Hello, everyone.
Al Morena is an applications engineer with Mott. He's been with us for 4 years, and he also comes from the valves market. So you have quite an extensive experience with flow control and aerospace. Is that correct?
That is correct, Dan.
All right. And my name is Dan Gallber, and I'll be moderating this webinar today. So I know a lot of you are current customers, but for those of you who are not familiar with Mott, I just wanted to give you a quick rundown of who we are and what we do. So we've been in business for 60 years, making products for many of the most demanding customers in the world, such as NASA and some of the largest companies in the world. Additionally, we have the largest install base of porous metal filters and fluid controls in the entire world, and a wide variety of industries, not just aerospace, but all the way down to implantable medical devices and semiconductor manufacturing. We also have the most extensive alloy selection, ranging from cryogenic temperatures all the way up to 3,000 degrees plus Fahrenheit. And additionally, we have a customer innovation center that's becoming a hub for customer design and process development, where we do a lot of lab testing to support our customers' design and development efforts. Our agenda for today is we want to review the principles of filtration and flow control. We want to understand porous metal and its capabilities. And then we're going to go through some overview of uses for porous metal in aerospace and defense. We're going to talk a little bit about next generation design and development in this market, and then we're going to do a quick wrap up. Just to note, we will not be doing a live Q&A for this session. The reason for that is we find that a lot of our customers have sensitive information that they would like to discuss, and we don't think that's appropriate for a public webinar forum. But if you do ask questions using your GoToWebinar sidebar there, those questions will be transferred to us immediately after the webinar, and we will respond to you through email as soon as we're able, likely within 24 hours. So feel free to submit the questions and we'll get back to you as soon as we possibly can. And additionally, you can download some resources there that we've uploaded for your leisure. But before we get into the presentation, I just wanted to let you all know that through the month of June, Mott is currently offering free on-site technical workshops for customers who qualify. The technical workshop includes us sending out 3 to 4 engineers to your site to teach you the latest in filtration and flow control, particle science, welding techniques. It's quite comprehensive, and we also have one-on-one design sessions for you and your engineers to speak with our engineers to solve some of your difficult, complex problems in filtration and flow control. So if you'd like to see if you qualify, feel free to contact a Mott representative to learn a little bit more. So with that being said, I'll do a little less of the talking now and turn it over to my engineers. We'll start talking about filtration basics. So Alan, Tim, do you want to quickly take the audience through how to design a filter and what are the key considerations that you think of when you're designing a filter?
So I guess to start off with, you're always looking for material compatibility, making sure the filter materials are compatible with the fluids that are going through it, or that it's being surrounded by it. Particle size distribution, really here you're looking for what media grade you're going to be looking to choose to give you the particle retention or removal efficiency that you're looking for. That leads us to the next one, filtration efficiency. The media grade you choose is going to give you the efficiency you're looking for. And then 2 important things that we get from you are the flow you're looking for and the pressure drop required. We take those items and try to make the best selections we can.
Okay. And what are some of the differences between gas and liquid particle capture?
Well, there are different mechanisms for capturing the particles, whether you're in a gas or a liquid. Gas filtration efficiency tends to be much higher than a liquid for the same media grade. As you can see from the graphs here, or the charts here, that the gas is going to be a much higher efficiency than the liquid, primarily because there are more capture mechanisms in a gas filtration application than a liquid filtration application.
Would I be correct in assuming, looking at these graphs, that determining filtration efficiency for gas is much more difficult than it is for liquid?
Wouldn't say much more difficult, but definitely there's more involved in a gas because there are several different types of capture mechanisms that are involved.
Okay.
One of the common misconceptions is for in a liquid, sieving is the only way to capture or filter particulate. While that is true for a liquid, it is not true for gases. There are other methods of capturing for gas.
And do you often, do both of you often encounter customers who believe that sieving is the only technique for filtration in gases?
Sometimes we do encounter customers like that, but just give them a little more insight, and they understand some of the other mechanisms that are possible.
Okay. So there's quite a bit of gas particle capture methods that I see on this. Do one of you want to take us through some of the alternatives to sieving that we have in gas particle filtration?
So I guess one of them is interception, right? Or a particle can go into the porous metal and be intercepted along the thickness of that metal or that porous metal and be picked off into the porous itself. So interception is just another type of a mechanism there.
What about maybe diffusion? Maybe can you educate some of the customers on what that is?
Sure. With the diffusion, the particle just kind of floats through the filter media until it finally gets captured by part of the element, which just kind of drifts into it by diffusion. Whereas the interception, the particle is flowing through the porous, and at some point it's going to come into direct contact with the filter media. And the reason it's listed twice is because it can happen very early on in the beginning, as it's starting to penetrate through the porous, or it can happen towards the end before it reaches all the way through.
I'm vaguely familiar with the terms of depth versus barrier filtration. Is that what we're showing in this slide here?
Sure, it's just to what Tim just said, right? As you go deeper into the porous media, the effects of interception are more prevalent because you're going through a larger thickness of that media to be able to grab those particles.
Okay.
So this particular graph just shows the different types of filtration mechanisms and their efficiencies. As you can see, interception, for example, doesn't work great for filtration efficiency on small particle sizes, but as the particle sizes get bigger, the filtration efficiency gets much better. Diffusion, on the other hand, is the exact opposite. It works great with small particles, but as those particles get bigger, the filtration efficiency drops off.
So so the summary of this graph would be interception, inertial, and sieving are great for particles that are larger, and then once you start getting into submicron, diffusion is often your best source for particle capture.
That's true, and I think one of the things it's showing here is that it takes many different types of mechanisms to give you the full filtration efficiency you're looking for.
And keep in mind, this is strictly for gases we're talking about. For liquids, it's going to be sieving, which means particles get captured on the surface of the filtration media.
Okay. So we'll move next on to flow control basics and some of the design considerations that we have when designing a flow control.
So essentially, when you're designing a flow restrictor, what you want to look out for is you want to have laminar flow coming through the porous. It needs to be accurate and repeatable. The hardware and the material of the restrictor has to be compatible with the application, with the gas or the liquid.
And what are some of the, so I know that two of the main methods of flow control are flow orifice and a porous metal flow restrictor. What do you want to quickly talk about, maybe the differences and why you'd use one instead of the other?
So an orifice would be really what it is it's a hole, and the gas is passing through a hole. Some of the negatives on an orifice is that if you have something in the gas stream and it plugs that hole, you basically close off the flow for the gas that's going through there. A Mott porous restrictor is going to have tens of thousands of pores in it, and if something covers one, you're still going to have that gas passing through the remainder of those pores in there. So it really gives you the ability to keep flowing even if you do have some particulate in the gas stream itself.
And one of the advantages for the orifice is eventually you'll get to a choke flow, whereas you increase pressure, the flow is not going to continue to increase. Whereas with a porous metal restrictor, as you increase the flow, you will increase the pressure, you'll increase the flow. On the other hand, it's calibrated for a specific pressure and a specific flow rate. So there's a large advantage to having it calibrated for a specific pressure and flow rate.
Okay. And I know each of you have designed probably hundreds, if not thousands, of restrictors for customers. Do you constantly, or I shouldn't say constantly, do you regularly run into customers who are using orifice that have problems with like high gas velocity and they're looking to replace it with a porous metal restrictor that could give them laminar flow? Is that something you somewhat regularly encounter?
I think that is, in times we do encounter that, where they're trying to replace an orifice with a restrictor because they want that gas exit to be more laminar, more streamlined, not as turbulent, I'd say.
So we'll move on to porous metal and its capabilities and give you a general overview of what porous metal is and how we design it and some of its versatility.
So a little bit about the porous metal. Really, you start with an irregular shaped powder. It's semi-compressed and then sintered. Once it's sintered, it takes on a rigid structure just like it would any other metal, but you do have the pores in there, and those pores are based on the size of the powder particle that's used to make it. We test that rigid structure using a bubble point test to verify that it's giving us the correct pore size we're looking for. And our range of pore sizes really run from 0.1 up to 100. That's really our complete range for porous metal that we manufacture here.
And so that powder can be used to make all those shapes that you see below in that picture?
That's correct, Dan. So that powder is used and put into a die and then pressed, and it gives you the shape of a disc or a cup or a sheet or a tube. Some of those basic shapes are what we do on a very regular basis.
Okay. And from my experience, I know we use porous metal in quite a bunch of different industries, ranging all the way from microelectronics, where we're talking parts per billion, filtration and gas, process systems, where we're filtering for refiners and chemical processing companies, and additionally some healthcare applications where we're talking medically implanted devices and lab equipment. But right here, we're talking more OEM industrial today. So why would a customer potentially use porous metal over other materials?
So I think the couple big ones that I run into is that they're looking for tight tolerancing, and they're looking for something that has high heat resistance and really the longevity, the ability to use the product for a long period of time and give you good service.
And I think that's an important factor, is the longevity. Especially when you get into some of the corrosive environments. The metal will withstand some of those environments better than some of the other materials that are used for filtration.
Okay. So typically there's probably some sort of spec that the customer has in regards to heat, pressure, corrosion, or something unique like that that would require them to use porous metal versus, let's say, a plastic or a cloth.
That's correct.
That's correct. And I know Tim and Al spend quite a lot of time customizing porous metal components for specific applications, for specific designs and unique specs. So do one of you want to quickly talk to customers about some of the customization options that we have for this material?
Well, essentially what it really boils down to is if you have some type of hardware that it needs to go into, we can probably design the porous to fit into it. We do probably 90% or more of what we do is custom designed for the customer's applications. It could be as simple as modifying an existing piece of hardware or designing a completely new piece of hardware to fit into your assembly.
And I see quite a bit of alloys listed there. Now, do you want to speak to maybe like what is most commonly used in aerospace and why would you use some of these alloys in different applications?
So the bulk of what we do is really in stainless steel, but the other alloys listed there are going to be give advantages in the application for maybe compatibility or temperature or weight savings. And that's really where those exotic metals come into play there. And we have worked with all of those and can supply those.
And what are we seeing at the bottom here in terms of these? It looks like microscopic images. What are we seeing here?
Well, these are just images of the different media grades, so you get an idea of the pore size from a media grade 0.2 on the left, and then working up to media grade 100 on the right. You can see the size of the holes are essentially get bigger.
And that's going to help determine your particle capture and how restrictive your part is for flow control application.
That's correct, Dan.
So let's quickly touch upon some porous metal applications for aerospace and defense. I know we're all the way from ground to space, so can you guys take us through maybe some of the general applications before we go into specific applications next?
So for ground, we do work in munitions and fuel cells. For air, it's typically fuel filters, air filters, and actuators.
And for space, typically it's either propulsion systems, transfer systems, heat pumps, or venting applications.
And a lot of times, I think from my experience, is that customers come to us when it's a mission critical application. So once you launch a satellite, you can't go back and replace your orifice. You need to have it right the first time. So
that's very true, Dan, that, the mission critical applications, and really, I think that's all rolls back to tight tolerancing, reliability, that longevity, that sort of thing.
And we were on the Cassini space probe, I think 20 years ago. So Al, you want to tell people a little bit more about this?
So this was a flow control restrictor put into the space probe and really used to control the flow of gas going to the propulsion to actually, steer or propel the satellite in orbit. And had to be done very accurately, and our restrictor did that work. And
then Tim, I know you know a little bit about this Earth satellite application. You want to take us through it?
Yeah, and this is kind of related to the application that Al was just talking about, in the sense that the filter is used to filter the propulsion gas. It needs to be clean. If they get any particulate in it, it will mess up the jets that are controlling the satellites. So they use our high purity filter, which will filter down to 0.003 microns at 9 log reduction. And we've been very successful with them over the years. I've been working with them since I've been here, and we've never had a failure. It withstands the shock and vibe that it needs to go through for launch.
Okay, and they've launched over 100 satellites since, so we must be doing something right.
Yeah.
Okay, and then next we have oxygen mask. So we, in the case of an emergency on an airplane, we actually protect consumers as well. We're not just satellites. So Tim, I believe you're familiar with this application.
Yeah, I like this application. I think it's a really neat application, in the sense that our flow restrictor is used to control the flow of oxygen. If your cabin pressure, if you lose cabin pressure and your oxygen mask falls and you put it on, you're going to have a piece of our porous metal between you and that tank of oxygen that's supplying the oxygen to you, and it's going to control the flow of the oxygen to make sure that you get the right amount.
Okay. And then lastly, we do work with munitions and missiles. So Al, you want to?
So the main application here is using disc filters to really filter the gas using the transfer system, the gas transfer systems in the missiles. Typically there's 2 or 3 typically on a missile, and they really make sure that the gas has got filtration before it goes from one side to the other, passes through from one side to the other.
Okay, and next topic we want to cover is next generation design and development. So Al, you know a little bit about 3D printed porous. Do you want to take the audience through this capability?
Sure, Dan. 3D printed porous, this gives us the ability to print porous in a manner that is non-traditional, without using traditional pressing methods. So really it takes away the limitations of the shape you're trying to create by pressing something. By doing that, you can basically come up with a shape that's only governed by your imagination. A couple other real advantages here are the fact that you can print solid hardware to the porous, and you don't need to use methods of attachment like welding or pressing. You make a homogeneous product, and you have solid and porous together. One last thing that's really unique about the 3D printed process is that you get really consistent density throughout the porous. When you're pressing, you always get a little bit of different densities when you're pressing at the edges. With 3D printing, you get consistent density from layer to layer.
Okay, and I see that it says lighter weight up there, and I know that's important to aerospace customers because you're trying to get a satellite off the ground or some sort of a plane off the ground.
Sure.
So can you explain maybe how 3D printed porous is lighter than traditional?
Sure. So the way it would be lighter there is that you'd be able to make a shape that could give you the exact size or dimensions you're looking for and not have to press something traditional that might be larger. They show a cone there. In traditional methods, you might have to press a cup, which would be larger in size and give you more weight. So you can print a cone and give you the reduced weight benefits.
So optimal use of space and geometry.
Yes.
Okay. And next we'll move to computational fluid dynamics, also known as CFD. Tim, you're familiar with this capability.
Yeah, this is a capability that we have developed. The beautiful thing about the CFD is it allows us to essentially get to a final design a lot faster. If you're looking for a flow filter with laminar flow throughout it, we can design the filter to meet those requirements, and allows us to see what the flow path is going to be and where the turbulence are going to be, and we can make adjustments to minimize those turbulences.
So faster design components and more accurate designs if we use this type of technology.
That's correct.
And then lastly, we have our newly commissioned Customer Innovation Center up and running. And the Customer Innovation Center, we've had, I'd probably say, close to 100 customers in the most recent year. And what we do here is we train engineers and scientists on the latest in particle science and give them some design consultations for some of the really tough problems that they're facing in filtration, flow control, or even sparging. And we have our rapid prototyping cell that allows them to create basic geometries and components and designs right on the spot. Sometimes we can turn around complex prototypes in as little as 2 weeks. It really depends on what the design is, but it allows us to be a lot faster with your design efforts. And additionally, we have our lab testing, which allows you to take whatever design that you have created and then test it to correlated conditions or run some basic tests to understand if you do have the right part for your design, and we can optimize it from there. So a lot of customers are using this, and we invite you all to use it as well. Alan, Tim, I know you've had a couple customers come through here. Is there any other things that you can add here?
No, I think, Dan, what you hit on is very good. It gives the customer the ability to come in, sit down, really talk about their application, and then go through some of the actual prototyping and hands-on testing to get that good feedback for it.
And I think that's the big thing about the CIC is that it allows us to sit down with our customers, have face-to-face meetings, and come up with the best design as quickly as possible, get the prototypes done, do some testing on it, so that when we deliver the product to the customer, they know what they're expecting and they know how it's going to work.
And that's going to wrap up our webinar today. I just wanted to quickly remind you that we are, again, offering free on-site technical workshops for qualified customers through the month of June. If you would like to see if you qualify, feel free to contact a Mott representative. We'll send a couple of engineers out to your site, teach you about the latest in filtration, flow control, particle science, and designing for manufacturability, as well as do some breakout sessions with your engineers and our Mott engineering team so you can overcome some of your complex filtration and flow control problems that you're experiencing. Okay, and thank you everyone. That's going to wrap up our webinar today. We'd like to thank you all for attending. I will note that we put our emails there at the bottom in case you have any direct questions for one of our presenters or for me. We'd be happy to speak to you about your application or any additional questions that you may have had stemming from the webinar. So feel free to contact us. We'd be happy to help you. Alan, Tim, any parting words for the audience today?
No, goodbye and thank you.
I'd just like to thank you for attending and have a great day.
Okay. Thank you, everyone, and have a great day. Bye.